Yeah. Okay, so we can get started. So today it's my pleasure to introduce Shuhang. Shuhang is a PhD student from Rutgers University, and he's currently working with us at the Red Hat AI Innovation Team as a summer intern. So his research spans a lot of topics. I guess one of his most focus is on making large language model system more reliable and controllable, with an application on RAG system and the agent framework. I'm really excited about his talk today because I was in a workshop at Stanford a few weeks ago, and the workshop was about agentic AI. And one important topic they've been talking about was, we all know LLM, right? Like I guess especially for the people in this talk, for people at Red Hat. So we know LLM is a very efficient ML system for serving large language model as a chatbot. But now, this year, people are moving to agentic AI. So one topic people from Stanford was talking about was, what would be a counterpart of LLM for serving agent? And I guess in today's talk, so Shuhang is going to talk about when large language model means agent, means cache. And one application we will talk about would be how we define cache for agent. Is it still going to be KD cache, or is it going to be something else? I think that's something Shuhang will tell us today. So without further ado, please take it away.
Okay. So hello everyone. My name is Shuhang Lin, and I'm very honored to be invited to give this talk. And today the topic I'm going to talk about is large language model means cache. So today I was going to mainly focus on how to build a cache for agents and make it more efficient. And here we go. First is the intro. So why we need a cache? And since Red Hat was open source system company, so I guess that everyone is very familiar with the cache. And the definition of cache is that cache is a small fast storage layer that can keep copies of reasonably frequently accessed data to enable rapid reuse and reduce access latency to slow backstores. And in a short way is that if you found that here is some data frequently used, and you can see that, okay, if I can find a way to reuse them and therefore to make system more rapid and more fast. So here, this is the motivation. So, and here comes to the questions. And now, since the large language model is very powerful, so why do we need a cache? So first reason is that the large language model is very computational consuming. This means that you need a lot of GPU or a lot of other resource to run a large language model. And therefore, it's very natural for us to come with some cache or something else to make it more fast. And here was another reason is that when we run a large language model, it's very naturally that we have a lot of long context. And for example, when you want to build a web browsing agent or web browsing large language models, and here was a very long HTML. Therefore, you have to think of a way to make it more efficient. And when large language model do reasoning, such like the DeepSeek or something else, and yet when it's doing reasoning, it has a long reasoning path. So you have to find a way to make it more efficient. And therefore, we can show that this is why we need large language model with cache. And another question is that how can we to use that cache into our large language models? So let's recall the definition of the cache. A cache is a very small, very fast storage layer that can keep the copy of the recently or frequently accessed data. And I think the most important part of this is that of the definition of cache is that the frequently and the recently accessed data. So I think the most important part for us to design a cache is from the most frequently parts or most frequent data in this system, and therefore we can try to reuse it. And and this is an overview of my talk. And I think that since I don't have enough time, so today I will mainly focus on the part one, how to design application layers for the large language model agent caching. So here we come to the part one. And I think like agent is a very popular concept today, and since every company want to launch agents or like use agent to help them to use their product, and so it's like agents is like can do something they are good at and help to do something. So like when you use the agents is when you using agents, like an agent always need some tool to help them to become more powerful. Or for example, here with some topic like tool using, like or just like teaching agent to use something like MCP service or like using some token to help them to do reasoning. And there was other technical like the RAG and help them to retrieve something that they may be used to help them to be able to access the external external knowledge base. And I was interested in like how can we build a cache for agent when they doing RAG. So here was like lots of in our papers. So in the traditional way, we can see that the left part, we can see that when agents have a query, they have to send the query to the knowledge base, and therefore the knowledge base will retrieve something for the base agent. And here comes the question: is this really efficient? I think the answer is no, and therefore we need a cache, and we will talk about this the reason why we need a cache later in more detailed reasons. In like new architecture is that when we agent have a cache, it will send the cache to the external knowledge base, and we have a like cache part. We can cache the most frequently used data in this cache, and therefore the agent can access this cache. Therefore, this pipeline is more efficient. And in a more real setting, we can say that if we have a huge knowledge base, and each agent, and we have a lot of agents, and each agent can build their own cache and makes their own pipeline more efficient. It's a little bit like distribution system, and it may be, yeah. So,
Zhuhang, can you go back to last slide?
this one?
Yeah. So, correct me if I'm wrong, but my understanding here is, so on the left figure, you have an agent which has access to a database, right? It could be some code base or it could be some customer documents.
Yeah.
And the agent is going to access the code base for multiple times because there might be multiple queries.
Yeah.
So here, you're saying the cache you define here will store the samples or maybe some passages, which will be reused quite often by the agent for different queries, right? That's how you define the cache. So it's a different thing compared with KV cache. Yeah. So it's more like in the data level or sample level.
Yeah.
Right.
Yeah.
Okay,
That's true.
Got it.
Yeah. Let's move to the next page. And so what we need a cache during is agent doing RAGs, and for the first reason is that nowadays knowledge base is quite huge and it will growing more and more larger. And for example, so we can see that the TB or GB level knowledge base is quite often in company or in apartment. And just like piles of documents in the government or in some companies. And the second reason is that we can see that we have like some like edge device, for example, like computers or something or smartphones or something else. So it's unable to load the full knowledge base on the edge device, since that we have TB or GB level knowledge base. And the second reason, and the third reason is that if we just like use the network connections to the external knowledge base, under some conditions, it's not very reliable. For example, like maybe you like in the wild, the network is not very reliable, and you want to use an agent, or maybe you use some in some companies that the network is not very good, and yeah, that's why we need like agents rather cache. So when can we build a cache for agents? The definition of cache is that how can we define the most frequently used data? And the reason why can we build a cache is that given like compared to pure large language models, our agent is much more domain specific. For example, if you have a medical agent, and you probably not ask this agent like pop star questions. Yeah, I think it's very makes sense, right? So we can say that for our agent, it don't use so like they don't use all knowledge base. What they need is just a small part of the knowledge base. So this is why we can build a small cache for agents. And here is example. Here is a medical agent, and maybe this medical agent is like most query for this medical agent is medical policies and some disease informations and some hospital informations. And you maybe not ask this agent about like pop star questions, like mathematical questions, yeah, and the second reason why we can build a cache is that in the last page we're talking about that what agent need is just a small part of our knowledge base, and in this page, in this slides, we will show you that we can use much smaller cache to make agent more efficient, because what agent really needed is much smaller parts. For example, if you have a medical agent and you can, it's very intuitive that all the medical information's passages is needed for agents. And we can show you that we cannot cache all about the passage related to like medical informations, and all we needed is the most popular passages, and can retrieve the nearly same result for this agent, because the retrieval frequencies is like the allowed to like a power law or something else. And here is the examples, and let's go through the right ones, and we can see that this is like maybe like popstar agents, and we can show that after go through all the queries, and the blue node means the passage we wanted, and the pink node means the passages of the noise, and we don't want it. And we can see that, firstly, we can see that here was a 1 point, extremely of high frequencies. And the second, we can see that most of the noise is of the low frequencies. It means that if we want to build a cache, and maybe we just like make the frequency to about 20 or 30 or something else, and we can like separate the noise, and what we really wanted. And the left part.
Oh, sure. So for this right figure, so can you clarify what you mean by noise? Are they like pure?
Okay. For example, so you have like this is a data set called Squad, and here was some queries, and there was a ground truth passage, and since like all the queries is about, in this example, all the queries about maybe a star Beyonce or something else, and therefore this means that all the passage really was labeled Beyonce as we wanted, and the passage with other label is the noise. Yeah, and here is an example of like medical agent, and we do the dimensional reductions, and the y means the frequency of the passage, and we can see that for this agent, most passages of low frequencies, while some topics is of high frequencies. And yeah, this is some observations. And on the left plot, we can show the power law, and on the right plot, we can see that's Hubness. And I will mention the Hubness later. And yeah, this means Hubness. Some passages extremely of high frequencies. And let's go to the next page. And here was like, so maybe you ask. Maybe you want to ask why some passages of extremely high frequencies, and here was, and I also do some experiments, and we can show that. Now we have our clusters. Maybe this class is all about Beyonce, and maybe class is all about semantic policies, and yeah, and now we calculate the hardness degree of each passage, and this means that. Each passage will point at the top K other passage more close to it, and then we calculate the hardness, and we can see that.
Wait, sorry, can you mention like what is the hardness degree? So for each passage you have its top K nearest neighbors.
Yeah.
Are you calculating the distance with the nearest neighbors?
No, if this is the top K, this was it has 1, and it's not top K is 0. And we calculate how much top K is and how much top K among all other passages.
Can you see this?
I can show the definition of the yeah, this is the definition of hardness.
And can you walk us through this definition?
Okay, yeah, and now maybe we have our clusters, and we have this passage and these passages, and we have other passages, and each passages will find the top K of their neighborhood, and if these passages are in this top K neighborhood of other passages, and yeah, this means that the degree will increase 1, and others, yes, yeah.
I see. So here, okay, I see. So here you are saying like to compute this hardness degree for one data point. So you go through all other data points from your database.
Yeah.
Each other data point will get its top k nearest neighbors, and you want to see among those top k nearest neighbors if the current data point you care about is within that top k nearest neighbor set, and then you iterate over all data points from your database.
Yeah.
Got it.
Yeah. And we can see that here was a relation with if a passage is more, it has higher Hubness score and is more close to the center of the clusters. And this doesn't really make sense because it's more central, and therefore every passage like to link with him. And here with some mathematical proofs to prove that in extremely high dimension. For example, like in embedding models, and it will map a passage to like 200 dimension tensors, and therefore, like in a 200 dimension space, and if a passage is more close to the center of the clusters, and it will have some much more Hubness than the others. And yeah, since we like discuss a lot about that, some passages much more frequently used in agents, and here always comes to questions. And is this yeah, and we can see that in the left plot, we can see this is the topic of the navigation systems, and in the red plot, this is the topic of the bacteria, and all this means that in the left ones, all the queries is about the data systems, and in the left ones, all topics about the bacterial ones. And we can show that in the left topic, and some passage is extremely high frequencies of the extremely high frequency used, and in the left ones, and we can see that this Hubness is not very appeared. And here with some reasons behind it. And firstly, because the query is this dataset is not large enough, and each topic is about just 200 or 300 topics, and if this domain of this topic is smaller, this means that maybe this is a term like Beidou, and therefore the embedding model will embedding this passage to a much smaller subspace, because this semantic meaning is not so much uniform, it's not so much general. Therefore, this means that the embedding model will map those passages in much smaller subspace. And when it comes to bacteria, is that means that the semantic we have the difference between the query is maybe become larger than the Beidou systems, and therefore the Hubness is not so much appearing. And the second reason is that the dataset is not so much smaller, and if you want to make the bacteria to appear extremely high Hubness score, you need more cache. You need more query numbers. And and now we how can we design a cache and the overall cache strategy this way, and we will explain this formula later. And the HK means Hubness score, and P means passage. and beta is parameters, and W means size of each passage. It makes sense because the passage is more larger, and the cost to cache them it become higher because, for example, if a passage is extremely high, if we cache them and we can't cache something else, and therefore we have to think twice before we cache them. And let's come to the first part and this part. Yeah, and this part we like to use the Hubness score we mentioned before, and this means that in a cache we can calculate the Hubness score of each passage, and we can if a passage have more Hubness score, it means that every other passage is like it, and it's more close to the central meanings, and therefore we should think twice before we delete it. And why we need log? Since I have mentioned that the Hubness degree is low power distributed, therefore we need log to do the uniform, to do the normalize, and yeah, this is the definition of the Hubness score. And secondly, is called the DRF. And the DRF means distance rank frequency, captured how often and how high ranked and semantic close a passage appears in the recent retrievals. And this is how we calculate the DRF. And let's explain it. And firstly, when you have queries, and it will go through the database and retrieve the top K passage needed, and therefore, each passage with rank, and for example, is the most close one to the query in the embedding space, and here was the top one, and the second top two. So here was rank 1, and the second rank 2, and something else. And since that other methods don't use rank information during the retrieval, therefore we decide that we want to use the rank information of this retrieval. And the second part is the distance between the queries and the passages. And this is because, for example, if because the rank is hard code, and for example, if so it was ranked top 1, and if the embedded space is very sparse, and each passage is very far away from the queries, and since maybe we don't want it, because otherwise, if the query is more related to the retrieve passage, and we just want it.
So here do you dynamically update this priority score, or maybe this distance rank frequency score? Because as more query comes in, you'll need to update this score for each passage. This is the score is the information of the DRF score is not calculated in the massive external data set, massive external knowledge base. It just calculated locally in this cache. Yeah. And how do you use this score? So you use this score to rank different passages in your cache?
Yeah.
Okay, and then for the passage which receives a low score, are you going to remove it from your cache?
Yeah. Now, for example, now you have a cache, and if the cache is full and we want to delete some passage, therefore you can like to add some new passage to the cache, and the score is to decide which cache we want like to keep it here and which cache we want to delete it.
And I guess maybe you are going to talk about that, but I wonder, once you remove some samples from your cache, how can you add new samples from your database and to your cache?
Okay. Yeah, that's a good question. And oh yeah. If we want like remove something else and we just end it, and something new retrieve.
But
And we like give the priority of the lowest score among those passages currently in the cache. Yeah.
And how can you decide which sample from your external knowledge database, like which passage to add to your cache? Because you don't compute this priority score for external passages, right?
Yeah, just the current retrieve passage.
Oh, okay, just the current retrieve passage. I see.
Yeah. And for the DRF, and we like to do a lot of experiments, and we calculated different versions of DRF before we decided which version is the best one. And here was the result of this experiment, and we can see that like the yellow one is finally we the DRF formula score we choose, and the X index means each X index means a topic, and the Y index means how good it perform to like to making a cache, and we can see that the yellow ones perform the best among all the results. So, and finally is for the cache strategy is that we need to calculate the cost for us to maintain a passage in cache, and if the passage if all the passage of same value and the passage is extremely high, and we should firstly like take it off. Yeah, and therefore the W is the cache cost, maybe the memory size or something else of each passage. And this is the algorithms of our cache designs. And firstly, we want the query which was which was go through embedding models, and we have the query vector Q and the external corpus D, and the C is the cache we want to build, and it has W max. This means a capacity of this cache, and we have the top K retrieve. This means that the retrieve result of this query, this queries, and this means shift tolerance. And when we put the queries to the embedding models, we can retrieve the top K result. And yeah, this means top K items of these queries. And okay, and this means that whether we go to send these queries to the external corpus or just to use the cache for these queries, and how can we decide it? We just like to the average similarity score among all the queries. If this query if the similarity score of this query is much higher than the past query similarity score, this means that we can just use the cache. And if the similarity score is much lower than the historical similarity score, this means that if we use a cache, the retrieve result is not very reliable. So we should go to the external corpus. So if you if you use the external corpus and for each passage of the each retrieved passage, you can firstly calculate the DRF scores, and then you if the cache is full and you decided to end it, and if not full, you just end it. And now you decide to whether you should take out some passages. And you use this one to decide which score you should take off. And this is the result. And like LFU and the GPT cache is the baseline, and the ARC is the method we proposed, and we can see that the cache capacity is extremely small compared to the external knowledge base, and we can see that the hidden rates will go higher and higher when the cache capacity become larger, and the red figures show that the red figures show how we build a cache when the query continuous come in. We can see that the hidden rate will continue will go higher and higher. This means that if we had enough query, we can build a great cache for each agent. And this is the baseline. The LFU and the FRFO is the most classic baseline in the cache design, and the proximity and the activity cache is some baseline to use some semantic information to build a cache. And and the GPT cache was to reuse the results from the semantic similarity queries, and it will deploy a custom designed eviction mechanisms. And for the metrics, we use AMAT. This is average memory access time, and the hit rate means that the total memory access it's the number of cache hit. The hit rate means that if we can find the passage we wanted in our external knowledge, if we should find this passage in the raw cache, and therefore we have the hit rate. And this is the result of our cache design, and we can show that basically our method is achieve total result among all other methods. And if we use the Hubness score, the method will even perform better. I think yes, mainly this is working out. I'm talking about. Is there any questions? I have left about 20 minutes for the questions.
So I have a question. So here you run two evaluation metrics, but have you ever run like real time, like kind of workload run time for running your algorithm?
I think we run the metrics of the AMAT on real time setting. It's just like we launch cross service, and we send queries through this service.
So this, can you go back to the definition of this a metric?
Yeah.
So, okay.
So it is evaluating latency. AMAT.
Yeah, the AMAT means latency of.
And it penalizes for any misses on cache.
Sorry.
AMT is hit time plus penalty if.
Yeah,
Yeah.
sure, yeah. Yeah,
So why would the hit rate improve with the cache?
okay. Let's give examples. For example, you have a medical agent,
Right.
and if you are a developer, so you should decide there was a huge knowledge base, and you want to decide, okay, which parts of the so the passage you want maybe is mostly frequently used in the future.
Mm.
Yeah, and if you don't have any historical information and you just do some guess, and if you have a lot of queries, and you can use this information to help you to do selections.
So the search is also changing. Like the search result actually changes if you use a cache. Is what you're
Yeah, but it will not change a lot since we have cached the most valuable ones.
saying. Right. Okay.
Yeah.
Okay.
And we can also show that some queries is
Hubness
frequently occur. And yeah, this means that if you cache those passages, you can simulate the basic results of the external knowledge base, even with a very small cache.
Hmm.
And we can also show that yeah, if we like to make the capacity to about 5 MB and the cache rate is like 30%.
Right.
Yeah. And this cache size is agent specific. If the agent is more focused on a certain topic, and you just need a smaller cache, and if this topic is much more general, and you more use you use like larger cache. And to extreme examples, and if we don't give any constraint on this topic, this is a pure large language models. We need all the external knowledge base.
If you are not constrained by the hit time, how does this compare against if I were to just search against the entire data store? Like if we compare searching against cache versus searching against the entire data store, if you're not constrained with the time, right? Is the accuracy, like the accuracy would be higher for if I get access to the entire data store, right? Or did you find that Hubness actually makes it?
Yeah, that's an interesting question. And I did observe some results that because the external knowledge base is very huge and it has a lot of noise, and therefore, if the embedding model is not good enough, and it will introduce a lot of noise to the result. And therefore, you can maintain a cache even with higher accuracy. And however, if the embedding model is good enough, and the cache will the accuracy of cache compared with no cache will decrease a little. Yeah, and this means that, for example, for this topic, the embedding model is not very good. The cache can help to increase accuracy.
That's good.
Is there any question from the remote audience?
No, no.
Okay, so I have another question. So I think you, at the very beginning of your talk, so you showed like a power law of the frequency of the passages you retrieve from your external knowledge database. So I wonder if you have any observed some interesting pattern of the most frequent passage and also less frequent passages.
Oh yeah, that's also great questions. And what I observed, I can show through this plot. Yeah, some passage is of high happiness degree. This means that this is nearly in the center of the clusters. So I have wondering why those passages was in the center of clusters. And yeah, I just print some passages and I found that if passage is more in the center of clusters and it has more general meaning of this topic. And like for example, if this class is about myself and the most central passage in the class is more about who I am and what I'm done and what I'm currently doing, and the passages with low happiness degree. This means that more detailed information of this class. For example, just like the small project I'm going in a certain time periods, and yeah, and this means that the center passage is more like a summary of this topic, and the more low happiness degree passage is more like some details or some like other like case or some side informations of this topic.
I see. Got it. Any other question from the audience in the room? I guess if there's no more question, let's thank our speaker. Okay. Yeah. Okay. And thank you all for joining us, either like in the office or remotely. I think we are going to